maybe I should start and ask you guys, what do you know about complex numbers? Oh, there's so many hands, it's hard for me to actually choose someone. Okay, go ahead, Brad. A mix between real and the word we're going to use is imaginary numbers. That's right. And actually, when I say a mix, I can even do better than the word mix. What kind of mix? Well, it's going to be a sum. So we're going to write the number of the form a plus bi, okay? And here, a is going to be called the real part, and b is going to be called the imaginary part because it's next to the I. So you guys have obviously learned about imaginary numbers before. You've probably learned a little bit about complex. Where did you guys first hear about these? You know? Algebra? Pre-algebra? Where? Where do you come across them? Yeah? X squared. It has to do with x squared, right? I mean, when I say an imaginary number, what do I mean? Can I have an example of an imaginary number? Because I kind of have to know where I'm at. Liza, you have an example? The square root of negative 1. We know we can't take a square root of a negative number. So we call it, what do we call it? I. We call it I. And then we know, so for example, what would I squared equal then? Negative 1, right? Because when you square a square root, it goes away. So this is kind of my definition of imaginary number. I need that to work with. It's kind of funny where imaginary numbers. I asked you where they came from for you. You know where they came from for all of mathematics. How many are familiar with the quadratic formula? Yeah, so were the ancient Babylonians, all right? So don't feel, well, they were. They could solve quadratic equations. But if they ever got a negative under the square root, they just stopped. They said, well, I guess there's no solution. Okay? We don't do that. We actually work it out. And you'll get an answer that looks, well, actually, the quadratic formula, remember that you get, if I put a plus or minus, does that make sense to you? Because in the quadratic formula, that's b squared minus 4ac under the square root, that's right after a plus or minus. There's two solutions. So what happened was the quadratic formula solves degree 2 equations. And you might say, well, what about degree 3 equations? Is there a cubic formula? You guys didn't learn about a cubic formula? Well, there is one. Okay? And it was discovered in the Middle Ages, around the 1500s. And there's this whole great story about this duel. These guys are like very, very competitive, let's put it that way. And one guy challenges another guy, embarrasses him, but the thing that happened was this. Somebody was solving with their cubic formula. And while they were solving, they got a square root of negative 121 in the numerator of their big fraction of the formula. But then what happened was they got a square root of negative 121 in the denominator. So you know what they did? They canceled them. And when they canceled them, they took the rest of the stuff, worked it out, and they got the solution to the cubic equation. And all the mathematicians, you can't do that. Well, yeah, I did. It worked. They checked it, it worked. This was the start, the first time that imaginary numbers had ever been used that we know of. Okay? Anyways, about 100 years later, a guy named Gauss does all kinds of work with, well, I'll show you what he did. You see, once you know the square root of negative 1, you guys know the square root of negative 4. What's that? Good. because it's I times the square root of 4, so it's just 2I. You guys with me? Can you have 3I? What would that be? The square root of negative 9. Can you have negative 5I? Would that make sense? Think about that one. Can you have 5I? What's that? Okay, now watch this. Put a negative in front of that. Can I do that? Yep, there's negative 5I. That's kind of interesting. You can't bring the negative into the radical, but you can have negative 5I. That's why this plus or minus really does make sense. Okay. Matter of fact, once you see you could do that, do you see you could put any number you want in front of the I? Could I have a half I? Sure, it'd be a half times the square root of negative 1, whatever it is. There is actually a whole imaginary number line. How many are familiar with the number line? Okay? So here's what I want you to do. Take your right hand, and in your right hand I'd like you to hold the real number line. Feel it. Look at it. Careful. It's infinitely long. You don't want to poke your neighbor. All right? But you have it. All right. Now in your left hand, take your imaginary number line. Okay? You're going to hold it. And I want you to look at it. And they look very similar. You notice? All right. Matter of fact, they share a point in common. Which one? I heard it. Why 0? Because what's 0I? Because 0 times anything is 0, right? And since they have that point in common, what Gauss did is he put them together. And he said, okay, guys, we're going to graph, and we're going to take the real number line, and we're going to take the imaginary number line, and just like I do everything else in algebra with graphing, I'm going to graph things, okay? So now if I have the number, say, 2 plus I, well, I'll come over 2, and I'll go up 1 in the imaginary direction, and that'll be the number 2 plus I. And so all of a sudden, all the complex numbers could be graphed, and the numbers that we're very familiar with are on the real number line. That's the real number line. And he developed beautiful mathematics with what is called, well, sometimes called the Gaussian plane, but nowadays it's usually called the complex plane. Okay, that's what this is. And if you had a good exposition to complex numbers in algebra, you probably got at least this much before. But there's a lot more to the story, and that's what we hit here in trig. Actually, some of the beauty in complex numbers you can't do until you get to trig. But now we can. You see, if I have the number 2 plus I, and if it's in a complex plane, oh, by the way, I should mention this, and Dr. Stitz does this in his book. He uses Z for complex numbers. One of the reasons he does that is because X and Y are already taken, right? We know X and Y are horizontal and vertical. And so some people will write Z equals X plus IY because then you're really on the plane, okay? Or W. I guess he also uses W. So if you see Z or W, that's probably a complex number, basically because the other variables were taken. All right. So let me give our complex number a name. What should I call it? Z. Exactly. Seems biased. All right. So Z is going to be 2 plus I. All right. And so now I can ask you some things. I can say, what is the real part of Z? Well, that's 2. That's the real part. And if I say, what's the imaginary part of Z, you would tell me, yeah, it's the coefficient of I is what it's going to be. So it's 1 in this case. It could be positive or negative. And basically, you know, those are the coordinates, aren't they? They're like the XY coordinates of that point. Okay? But now I might ask you something else. I might ask you guys, there you go. What's that symbol around that Z there? absolute value. Now, what am I going to mean? What does absolute value mean with real numbers? How far you are from 0. Distance from 0. And that's why absolute values are always what? Positive. Okay? So we still want that to be the case. We want it to be absolute value is the distance from 0. And so on the picture, I want to measure this distance right here. Of course, we were just doing that, right? What is that? Isn't that my r? How do you find r? Well, don't you do the Pythagorean theorem, right? So if I want to get the absolute value of z, that's the same thing as r, really. And so what's it equal? Well, it's going to be the square root of, why don't I say a squared plus b squared, where a is the real part and b is the imaginary part. He might use x and y. I can't remember right offhand in the book. I'll have to look. But the point is that the magnitude of z, there's that word again, right? Or the absolute value of z would be, in my example, the square root of 2 squared plus 1 squared. We get the square root of what? 5. So that's the absolute value of a complex number. All right. One more thing to show you, and that is what's called the argument of z. So yeah, if you want to call that the modulus, that's great. All right, and he gives you some rules here, some properties. That's nice. Here we go. The argument. Okay, so before we give the properties, we need a definition. It must be up above. There it is. So the argument is going to be the angle theta. Actually, what angle do you think I'm talking about? Let's go back to my picture. Well, hold on. There it is. Do you guys see the theta I'm talking about? This rotation right there. Theta. Since you guys just did polar coordinates, that's why I can actually talk about this stuff. We can write this as 2 plus I, but we can also talk about its polar form. Square root of 5. And then how do I get that theta? What's the equation that's going to give me theta? See, the argument of z is going to be theta. And I heard you say y over x. I know what you're thinking. You're thinking about what? The tangent of theta, of course, is equal to y over x. Too bad my little thing's in the way there. That's right. The tangent of theta is equal to y over x. And so, how many solutions are there to this green equation? All right, let me write it down. For us, the equation is tangent of theta. What's my y? My y is 1. Yeah. And my x is 2. How many solutions are there to this equation? Infinitely many, right? Can you name one of them? One of them, one solution would be the arctan of 1/2, okay? That's one of the solutions. Anyways, if you happen to use the one that's the arctangent, we call that the argument of z with a capital A, because what's special is that you know where we are. What do we know about capital argument? We know that theta will be between two values. What is it going to be between? for arctangent? What's the range of the arctangent? What quadrants is the arctangent? Give us an angle.
1 and 4.
1 and 4. So now what angles? Negative pi over 2 to pi over 2, okay? And if you, and again, my little clock is in the way there, but if we go back and look at the book, take that back. He says theta's between negative pi and pi. Yep, and I see what blew me away is that if you look at my example, I thought, well, I'll just take the inverse tangent of a half and I'll get the answer. I'll get what theta is. The problem is that that works for this example, but what if you give me a complex number like, you know, negative 3 plus 2i? What if we graph negative 3 plus 2i? What quadrant are we in if we do negative 3 plus 2i? Well, now you're in quadrant 2, aren't you? And so if you're over here, right, and say that's my negative 3 plus 2i, do you see how theta is going to be bigger? We want to always either rotate that way or this way. And so, yeah, I'm going to take back what I said and correct it, and I'm going to say that the argument of z will always be an angle between negative pi and positive pi, just to make sure that you can get any point in the plane you want. Okay. And I guess I'll make this one an equal to so that I could also get things on the negative x-axis. Okay. Question? That's our range of capital argument, yeah. Lowercase argument, that just means any angle you want. But if we do capital argument, we're saying, hey, let's keep it there. So I think at this point, you probably have enough tools to do exercises 1 to 20. Find a real part, an imaginary part, a modulus, an argument, and a capital argument. That's what I just did an example for. I'm not sure you have enough tools yet to do 21 to 40. Well, you do, but you just don't know it. Okay? So I need to help you with that. So here I go. What I'd like to do, guys, is I'd like to explain what you do with this modulus and this argument. So let me kind of continue with the same example. All right, what was the complex number we had? Z equals what? 2 plus I. Okay? And now we figured out the modulus of Z was the square root of 5. And we figured out that, what else did we figure out? Oh, we figured out that the argument of Z was, well, the arctan of a half. So we computed that, right? And so now what I'd like to do, and again, I can call this theta if I want. What I'd like to do is write the polar form of the complex number. Okay? Now I know that Z is equal to 2 plus 1I. Right? Where I kind of puts me in the y direction. Okay? So it might make sense to you that what I'm going to do here is I think about the x direction being r cosine of theta and the y direction being r sine of theta. Right? Where theta here is the arctangent of a half. So that gives me the angle that I want to rotate. Okay? And so what I get is I get the polar form for complex numbers. Okay? And so what it's going to be is this. Z equals, see, how do I say this? When I do x plus iy, it's r cosine theta plus I r sine theta. And so what do you factor out? You factor out the r. And you get cosine theta plus I sine theta. Now wait a minute. We have another name for r. The other name for r is the magnitude or the modulus of z. Okay? And then what I'll have is I'll have cosine theta plus I sine theta. Dr. Stitz likes shorthand, so he just says z equals, well, modulus z, and then he writes cis theta. So when he writes that, that's just really shorthand for writing cosine theta plus I sine theta. So, my example of green that I did before, when I have 2 plus I, another way to write it is 2, oh no, not 2, what's the modulus of 2 plus I? Square root of 5, cis, and then I'd have to work out what the arctan of 1/2 is. But this is another way to write complex numbers. So, I guess what I didn't quite get to quite is how you go back. But you have what you need. If you looked at 34, 2 cis of 7 pi over 8. That's the last thing to show you. Z equals 2 cis of 7 pi over 8. If I say, hey guys, I want you to write the x and y coordinates, all you have to do is this. We know x is our cosine theta. We know y is our sine theta. So what would I do to get x? 2 cosine of what? 7 pi over 8. And I would do 2 sine of 7 pi over 8. And I can go back and forth this way. That's all we're going to have time for, I think. So I may modify the homework, and I'll